Hello, dear friends. Today we're embarking on an amazing adventure through our solar system, a unique and dynamic structure that formed billions of years ago and still holds many secrets. We'll explore how the solar system is arranged, where it's located in the universe, and why studying it matters. Get ready for an exciting dive into the world of science and history. The solar system is a grand gravitational mechanism centered around our star, the Sun. It consists of 8 planets that orbit the Sun, over 200 known moons, countless asteroids, comets, and interplanetary dust. All these objects are bound together by gravity, forming a complex and harmonious structure. The size of the solar system is hard to grasp, especially when considering the Oort cloud. Its diameter can reach 2 light years, roughly equal to 19 trillion kilometers. If we imagine the Sun as the size of a soccer ball, Earth would sit 30 meters away and be the size of a pinhead. About 450 million years ago, a massive gas and dust cloud began to collapse under gravitational forces. A dense core formed at the center, becoming the precursor to the Sun, which soon started shining due to nuclear reactions. The remaining material created a rotating disk from which planets, moons, and other celestial bodies gradually emerged. This process is key to understanding how star systems form in our galaxy. The solar system serves as a unique laboratory for studying processes happening in other star systems. As for our solar system's place in the galaxy, it resides in the Milky Way, which contains between 100 and 400 billion stars. We're located in the Orion spiral arm, about 27,000 light-years from the center. This region is quite calm, likely fostering conditions for life. The spiral arms are bright, twisting areas filled with star formations, gas and dust. Our position offers relative safety since we're far from the active galactic core. The solar system moves around the galactic center at about 828,000 kilometers per hour. However, a complete orbit takes between 225 and 250 million years, known as a galactic year. We were in this part of the galaxy when dinosaurs roamed Earth. If you could see the Milky Way from afar, the solar system would appear as a barely noticeable dot among billions of stars. Yet, on that tiny dot, life began, a phenomenon we haven't found anywhere else in the universe. In the history of astronomy, our understanding of our place in space has changed dramatically. In ancient times, people believed Earth was at the center of the universe. This idea was based on the geocentric model proposed by Ptolemy, which dominated astronomy for about 500 years. According to this model, all celestial bodies, including the Sun and Moon, revolved around Earth. However, a significant shift occurred when Polish astronomer Nicholas Copernicus hypothesized that Earth isn't the center of the universe, but merely one of the planets orbiting the Sun. This discovery laid the groundwork for a new heliocentric model. Despite resistance rooted in long-held beliefs about humanity's place in the cosmos, Copernicus initiated an astronomical revolution. The next key milestone came from Galileo Galilei in the early 17th century. Using an improved telescope, he became the first to observe the Moon and see its craters and mountains, contradicting notions of its perfect sphere. Galileo also noticed the phases of Venus. This became strong evidence for the heliocentric model. These discoveries confirmed Copernicus's hypothesis and prompted a re-evaluation of astronomical foundations. Isaac Newton completed this process in the late 17th century with his laws of gravity. He explained why planets orbit the Sun and showed that gravity keeps all celestial bodies, from the Moon to distant planets, in their orbits. His work laid the groundwork for classical mechanics and allowed for more precise predictions of planetary motion. From the late 19th century, especially in the 20th century, a new era of practical space exploration began. In 1969, a program sent humans to the Moon. With the development of spacecraft and telescopes, people started to actively explore not just nearby, but also distant corners of the universe. A telescope launched in 1990 opened new horizons, providing astronomers with incredibly accurate data about stars, galaxies, and other cosmic objects. Thus, the journey from the geocentric model to modern scientific views of the cosmos has passed through numerous discoveries and revolutionary ideas. Now that we've covered the main stages in the development of astronomy and our understanding of space, let's focus on the planets closest to the Sun, known as the inner planets. These include Mercury, Venus, Earth, and Mars. These planets form a unique group of rocky bodies that differ significantly from the gas giants of the outer solar system. Mercury is the planet closest to the Sun, and everything happening there relates to its proximity to our star. It's about 0.39 astronomical units away, just under half the distance from Earth to the Sun. If 1 astronomical unit equals roughly 150 million kilometers, Mercury sits an average of only 58 million kilometers from the Sun, making it the first planet in our solar system. Mercury is a dwarf among planets. Its diameter is about 4,800 kilometers, which is roughly 2.5 times smaller than Earth's diameter. Despite its small size, it's denser than many other planets due to its large iron core. Mercury completes a full orbit around the Sun in 88 Earth days, making its year the shortest among all planets. However, a day on Mercury, or one rotation on its axis, lasts 59 Earth days. Due to complex interactions between its rotation and orbit, one solar day on Mercury lasts significantly longer. This unusual phenomenon is linked to orbital rotational resonance. For every 3 orbits around the Sun, Mercury rotates on its axis twice. This resonance occurs due to tidal interactions that gradually slow the planet's rotation. Mercury experiences extreme temperature variations between its day and night sides. The daytime side heats up to 430 degrees Celsius, enough to melt lead, while the nighttime side cools down to 10 degrees. This temperature contrast is one of the most extreme in the solar system. Mercury's system mainly consists of metal, and its core occupies about 3/4 of the planet's total diameter. This core, largely made of iron, likely exists partially in a liquid state. It creates a weak magnetic field, about 100 times weaker than Earth's. Nonetheless, even this minor magnetic field forms a magnetosphere that interacts with solar wind. The planet's outer shell, or crust, is very thin. Its thickness is around 20 kilometers. Mercury's surface is covered in craters, formed by intense bombardment from asteroids and meteoroids in the early years of the solar system. One of the most impressive craters, Caloris, has a diameter of over 1 kilometer and is so large that the impact that created it caused significant changes in the terrain on the opposite side of the planet. Studying Mercury began with a mission conducted in the 1970s, when a spacecraft sent back the first detailed images of the surface and discovered the existence of a magnetic field. However, a revolution in understanding the planet came from a mission that entered orbit in the 2000s. It gathered data on surface composition, measured the magnetic field, and revealed many geological features. Mercury is key to understanding the early history of the solar system, since its surface has hardly changed over billions of years, preserving traces of planetary formation processes. Its unique structure and dynamics provide scientists with vital information about interactions and the influence of stars on nearby planets, as well as about the cooling processes of planetary cores. Next on our journey is Venus, a mysterious planet known for its harsh conditions, often referred to as hellish. Venus is the second planet from the Sun and is Earth's closest neighbor. In size and mass, it closely resembles our planet, often called Earth's sister, but this similarity ends with numbers. Venus is a true cosmic hell where unbearable heat, acidic clouds, and atmospheric pressure can crush any earthly device within minutes' reign. However, Behind this extreme environment lies a story that could reveal Earth's fate if its balance were disrupted. Venus has a diameter of about 12,000 kilometers, only about 5% smaller than Earth's. Its mass is roughly 82% that of our planet, and its density and gravitational force are also similar. If you stood on its surface, your weight would be almost the same as it is on Earth. Venus is about 0.72 astronomical units from the Sun, equivalent to 108 million kilometers, closer than Earth, but not enough to explain its incredibly high temperatures. The main reason for the catastrophic conditions on Venus is its unique atmosphere, which consists of 96% carbon dioxide, with small amounts of nitrogen and traces of sulfur compounds. The upper layers of the atmosphere are covered by thick clouds of sulfuric acid that block sunlight, giving Venus a bright and shiny appearance in the night sky. These clouds reflect up to 70% of solar radiation. On the planet's surface, atmospheric pressure is 92 times greater than on Earth, corresponding to the pressure you would experience diving 1,000 meters underwater. If we tried to build a base on Venus, it would be crushed instantly. The surface of Venus is the hottest among all planets in the solar system, reaching temperatures of 470 degrees Celsius, which is higher than on Mercury, despite Venus being farther from the Sun. The primary cause of these extreme temperatures is the greenhouse effect, which completely altered the planet's atmosphere and climate. In the past, Venus may have had conditions more akin to Earth's, possibly even liquid water. However, the proximity to the Sun and high levels of solar radiation led to rising temperatures, water evaporation, and the accumulation of greenhouse gases, exacerbating the greenhouse effect. Venus's atmosphere is unique in that nearly 100% of thermal energy entering the planet results in around 70% of sunlight being reflected, while the 30% that penetrates is absorbed by the surface and cannot escape into space due to the dense layer of carbon dioxide. This process turns Venus into a real thermal trap. The temperature on Venus is stable across almost the entire surface, with minimal fluctuations between day and night sides, as well as between the equator and poles. This is due to the high density of the atmosphere, which evenly distributes heat. Even at night, when the sun doesn't illuminate the surface, the temperature remains nearly the same as during the day. Beneath Venus's clouds lies a fascinating world. Radar technology has explored the planet's surface, as standard optical methods yield no results due to the clouds. Venus is a planet of volcanoes, with its surface almost entirely covered by lava plains formed by past eruptions. One of the highest points on the planet includes mountains reaching heights of about 11 kilometers, higher than Mount Everest on Earth. However, much of Venus's surface is flat and dotted with strange geological formations, such as coronae, large rounded structures formed by magmatic activity. These coronae are remnants of tremendous tectonic processes that occurred billions of years ago. Despite the presence of volcanoes and lava, there are no obvious signs of tectonic plate movement, as seen on Earth. Instead, its crust bends and breaks under the pressure of magma, creating unique landforms. At about 60 kilometers above the planet's surface, incredibly strong winds blow at speeds of up to 360 kilometers per hour. This phenomenon is called superthermal wind. Venus rotates very slowly on its axis, taking 243 Earth days to make one complete turn, which is the slowest day among all planets. A year on Venus lasts only 225 days, making its day longer than its year. Venus was one of the first planets studied with spacecraft. Soviet missions were the first to send probes to its surface. These probes transmitted data from the surface, but operated for no more than 30 minutes due to unbearable heat and pressure. Later, a European Space Agency mission studied the planet's atmosphere and dynamics, including the chemical composition of the clouds. new missions are planned to investigate the terrain of Venus and its internal structure. These studies will help answer whether Venus could have been habitable in the past. Next on our journey is our home planet, Earth, where we'll discover what makes it unique and the only known home for life. On Earth's surface, liquid water occupies about 70%. Oceans, rivers, and seas are the basis of life. Water has unique properties, such as high heat capacity and the ability to dissolve various substances, making it ideal for sustaining biological processes. But what explains the presence of liquid water on Earth, unlike Venus and Mars where it's absent? The answer lies in Earth's location. It's positioned in the so-called habitable zone. The area around a star where temperatures allow water to remain liquid. If Earth were closer to the Sun, it might resemble Venus. If it were farther away, it could turn into a cold desert like Mars. Equally important is the magnetosphere, the magnetic field that shields the planet from solar wind and cosmic radiation. It forms due to the movement of the liquid iron core inside the Earth and acts as an invisible shield. Without a magnetosphere, solar wind could strip away the atmosphere, like it did with Mars. The solar wind is a stream of charged particles continuously emitted by the Sun, moving at speeds up to 800 kilometers per second and spreading throughout the solar system. It interacts with the planets, causing various phenomena. For instance, on Earth, the solar wind creates auroras and interacts with the magnetosphere, protecting us from its destructive effects. Earth is a dynamic planet. Its surface constantly changes due to tectonic processes. The Earth's crust is divided into several large and small tectonic plates that float on a liquid layer of the mantle. These plates move, collide, and separate, causing earthquakes and forming oceanic trenches. Plate tectonics plays a crucial role in the cycling of materials on the planet. Carbon dioxide released by volcanoes supports the greenhouse effect necessary for retaining heat. The movement of plates also renews the Earth's crust, maintaining long-term stability. Volcanoes, despite their destructive power, provide new materials for Earth's surface, releasing gases like carbon dioxide and water vapor that influence climate, along with minerals that enrich the soil. The Earth's atmosphere is another vital feature. Its composition perfectly suits the support of life. It consists of about 78% nitrogen, 21% oxygen, and trace amounts of carbon dioxide, argon, and other gases. This balance isn't random. It developed over billions of years of biological and geological processes. Oxygen appeared in the atmosphere thanks to ancient microbes about 250 million years ago, changing the planet's chemical makeup and making it suitable for complex life. Although carbon dioxide constitutes only a small part of the atmosphere, it plays a crucial role in regulating the planet's temperature through the greenhouse effect, preventing it from freezing. This fragile balance, which provides comfortable living conditions, is vulnerable. Any significant changes in carbon dioxide concentration could trigger climate disasters, as happened on Venus. Speaking of our moon, we can't overlook its essential role in stabilizing Earth and fostering life. The moon, with a diameter of about 3,470 kilometers, is the largest satellite in the solar system relative to its planet. Firstly, the moon stabilizes Earth's axial tilt, ensuring stable seasons and climate. Without the moon, the axial tilt could vary significantly, leading to climate changes. Secondly, the moon causes tides, which affect coastal ecosystems and may have aided the emergence of terrestrial life by providing an environment for adaptation. Thirdly, by absorbing impacts from asteroids and meteoroids, the moon served as a shield for Earth during the early history of the solar system. The next planet we'll explore is Mars. This close neighbor can tell us about Earth's past and its future. Mars, the fourth planet from the Sun, is located an average distance of 228 million kilometers, about 1.5 times further than Earth. Because of this, Mars receives significantly less heat and sunlight. Its size is half that of Earth, and its surface area is comparable to the land area of our planet. Mars' mass is only about 11% of Earth's mass, and gravity on its surface is roughly 38% of Earth's. This means if you weigh 70 kilograms on Earth, you'd weigh just 26 on Mars. Mars is a frozen desert with an average temperature of minus 63 degrees Celsius, but it can range from minus 125 degrees at the poles in winter to plus 20 degrees at the equator in summer. These drastic fluctuations are due to a thin atmosphere that hardly retains heat. Mars' atmosphere has a pressure of only 0.6% of Earth's, comparable to conditions at an altitude of 30 kilometers above Earth's surface, where commercial airplanes fly. It consists of 96% carbon dioxide, with small amounts of nitrogen, argon, and traces of oxygen and water. One of Mars' most impressive features is its dust storms, which can cover the entire planet, lifting fine dust into the atmosphere, blocking sunlight and making Mars even colder. The largest recorded storm in 2018 lasted several months and led to the shutdown of the rover. However, the surface of Mars is an incredible sight. Oxidized iron, enormous volcanoes, dried riverbeds, and icy caps at the poles tell the story of a planet that once looked very different. Imagine Olympus, the tallest volcano in the solar system, standing 22 kilometers high. That's 3 times taller than Everest, and its base is so vast that you couldn't see its peak. Among the expansive landscapes of Mars lies an impressive network of canyons stretching 4,000 kilometers long and reaching depths of 7 kilometers. This is 10 times the dimensions of the Grand Canyon and 4 times its depth. Scientists believe such formations could have arisen from tectonic processes or from water flows that once existed on the planet. Despite the absence of liquid water on the surface today, we see abundant evidence of its presence in the past. Billions of years ago, Mars had a warmer climate and a dense atmosphere. Rivers flowed in its depths and lakes formed. An ocean may have covered a significant portion of its surface. Nowadays, water on this planet exists only as ice at the polar caps or beneath the surface. However, it's believed that beneath the frozen soil layer may lie underground lakes of liquid water, especially in the southern polar region. These findings inspire hope that life may have existed on Mars in the past and possibly continues to exist today. Today, Mars is a priority target for space exploration. Rovers like Curiosity and Perseverance continue to study the planet's surface, gathering information about the climate, soil composition, and traces of ancient life. Curiosity, operating since 2012, confirmed that Mars may have once supported life, while Perseverance, which arrived in 2020, is exploring Jezero Crater, the site of an ancient lake and river delta that likely contributed to the development of microbial life. Humanity's ambitions don't. That it would be difficult to see even from a short distance. The rings consist mainly of water ice, with some rocky material mixed in. Their formation remains a mystery, but scientists believe they may be remnants from comets or moons that broke apart. Saturn's rings stretch out thousands of kilometers from the planet, but they're surprisingly shallow. Despite their beauty, these rings are not permanent. They constantly change due to gravitational interactions and collisions. Over time, they might dissipate into space. Saturn's atmosphere is another fascinating aspect. It's mostly hydrogen and helium, similar to Jupiter's. The planet experiences extreme weather, with winds reaching up to 1,800 kilometers per hour. The most prominent feature of Saturn is its hexagonal storm at the North Pole, a striking geometric pattern that intrigues scientists. Its size is comparable to 2 Earths, and it rotates with astonishing stability. Saturn also has a complex system of at least 82 moons. each with its own unique characteristics. Titan stands out as the largest moon, even bigger than Mercury. It has a thick atmosphere and lakes of liquid methane, creating an alien landscape. Europa, a moon of Jupiter, and Titan are leading candidates in the search for extraterrestrial life thanks to their potential subsurface oceans. As we move further into the solar system, we leave Saturn's splendor behind. Our next destination will be the icy giants, Uranus and Neptune, shrouded in mystery and wonder. These two planets are vastly different from the gas giants we've just explored. Uranus rotates on its side, giving it a unique tilt, while Neptune boasts the strongest winds in the solar system. Together, they represent the far reaches of our celestial neighborhood. The journey continues, and with each planet, we uncover more about the wonders of our universe. The profile almost disappears. Scientists continue to debate the origin of the rings. They might be remnants of a destroyed moon or material that couldn't form a full moon due to the planet's gravity. The rings contain interesting formations, such as the Cassini division, a massive gap about 4,800 kilometers wide that separates the ring into two parts. Saturn's moon Mimas is responsible for this gap as its gravitational influence sweeps particles from the area. Saturn's atmosphere mainly consists of hydrogen and helium, with traces of other gases giving the clouds yellowish and golden hues. While Jupiter has its famous Great Red Spot, Saturn boasts a similarly mysterious hexagonal storm at its north pole. This phenomenon is a gigantic hurricane, measuring 25,000 kilometers across, with a strictly geometric hexagonal shape. Within this storm, winds reach speeds over 500 kilometers, and its edges are astonishingly sharp, as if drawn with a ruler. Scientists still don't understand why the hurricane has this shape. Additionally, in 2010, Saturn's northern hemisphere unexpectedly changed color from bluish to golden due to photochemical reactions caused by sunlight. When summer arrived in that region, ultraviolet light broke down the molecules that gave the atmosphere its blue tint, turning the clouds yellowish. Saturn isn't just a planet, it has 83 moons, with Titan standing out. Titan is one of the most remarkable objects in the solar system, the second largest moon after Ganymede, larger than Mercury, and the only moon with a dense atmosphere. This atmosphere makes it unique. If you stood on the surface of Titan, the sky above would be orange-yellow, and the landscape would consist of plains covered in frozen hydrocarbons. Titan experiences rain, but not from water. It rains liquid methane and ethane. Temperatures are about 10 degrees below zero, making water solid as rock, while rivers, lakes, and seas consist of hydrocarbons that remain liquid at those temperatures. This world astonishingly resembles Earth. It has seasons, clouds, and precipitation, with rivers and lakes changing with the seasons. We can observe some methane seas gradually evaporating, while new bodies of water appear elsewhere. But the most intriguing aspect is that beneath Titan's surface, there might be an ocean of liquid water, creating conditions potentially suitable for life. While Titan captures attention with its atmosphere, another of Saturn's moons, Enceladus, stuns with its geysers. This small world, only 500 kilometers in diameter, proves incredibly active. Spacecraft have detected jets erupting from Enceladus's south pole into space, forming clouds. These geysers are so powerful that their particles contribute to one of Saturn's rings. Beneath Enceladus's surface also lies an ocean of liquid water, containing organic molecules and signatures of chemical reactions that could provide energy for life. This makes Enceladus a prime candidate in the search for extraterrestrial life in the solar system. The most detailed studies of Saturn and its moons were conducted by the Cassini-Huygens mission, launched in the 1990s. It spent 13 years in Saturn's system, transmitting thousands of images and unique scientific data. The Huygens probe, separating from Cassini, landed on Titan, becoming the first spacecraft to touch down on the surface of another planet's moon. It sent back images of orange haze, rocky plains, and signs of ancient rivers. In 2017, Cassini concluded its mission, diving into Saturn's atmosphere and transmitting data until the very last moment. Saturn is the last of the gas giants, followed by Uranus and Neptune, icy worlds that hold just as many mysteries. These planets possess powerful winds, strange magnetic fields, and moons that may harbor oceans beneath their surfaces. After exploring Saturn, our journey continues deeper into the solar system, towards the ice giants. Uranus, the seventh planet from the Sun, despite its smaller size compared to Jupiter and Saturn, impresses with its uniqueness. It seems to break all the rules. Blue, mysterious, tilted on its side, surrounded by rings and moons with astonishing relief. Its cold and harsh atmosphere conceals mysteries that remain poorly understood. This planet primarily consists of gases. However, it has significant differences. While the two largest worlds in our solar system are mainly composed of hydrogen and helium, Uranus and its neighbor Neptune belong to a different type, ice giants. This means Uranus contains significantly more heavy elements, such as water, ammonia, and methane, unlike the hot metallic hydrogen found in Jupiter's interior. Deep within Uranus lies a vast icy layer composed of these substances. If you began descending into Uranus's atmosphere, you'd first pass through its upper clouds, mostly made of methane and hydrogen. Then, pressure would increase and the gases would compress, turning into liquids and icy layers. But if you ask if Uranus has a solid surface, the answer would be no. The atmosphere smoothly transitions into deep layers, and the only area that could be considered a surface is the layer with pressure similar to that at Earth's surface. At Uranus's center likely lies a rocky core comparable in size to Earth, covered by a thick layer of hot ice. Temperatures in its depths can reach 5,000 degrees Celsius, but the thick layer of ice keeps the heat contained. This is why Uranus is one of the coldest planets in the solar system, with an average temperature of minus 22.5 degrees, even colder than the more distant Neptune. The reason is that Uranus hardly emits internal heat, unlike other giant planets that gradually release energy. One of Uranus's most surprising features is its unusual rotation. All other planets rotate more or less vertically, while Uranus tilts nearly 98 degrees. This means it literally rolls along its orbit, with its poles facing the Sun at times and then plunging into complete darkness. This creates extreme seasonal changes on Uranus. While winter and summer on Earth change every few months, one pole on Uranus can face the Sun for long years, followed by 42 years of night. Scientists believe that during the early stages of the planet's formation, a massive object, possibly a planet-sized body, collided with Uranus. This impact altered its tilt, causing Uranus' rotation to differ significantly from other planets. Despite appearing as a calm blue sphere, its atmosphere is quite dynamic. It's mainly made up of hydrogen, helium, and 2% methane, which gives the planet its distinctive color by absorbing red light and reflecting blue and green. Uranus's atmosphere hosts fierce winds reaching speeds of 900 kilometers per hour, surpassing hurricane speeds on Earth. Sometimes giant clouds form in the atmosphere, and while rings are typically associated with Saturn, Uranus has rings too, but they are much thinner and darker, made of particles that poorly reflect light. However, true wonders lie among its 10 moons. The most unusual of them is Miranda. This moon astonishes with its massive fractures, ledges, and chasms covering its surface. Some canyons on Miranda are deeper than the Grand Canyon on Earth. Scientists believe Miranda once shattered due to a powerful collision, but its fragments later reassembled, forming this chaotic world. So far, the only spacecraft that ever approached Uranus flew by in 1986. It passed the planet and sent back the first and only close-up images. Since then, no spacecraft has visited Uranus, but scientists are planning a new mission, possibly in the 2030s. The space agency intends to send a probe capable of studying the atmosphere, moons, and internal structure of the planet in detail. After the icy and mysterious Uranus, our journey continues to Neptune, the last of the known giants in the solar system. Neptune is the most distant, windiest, and arguably the most mysterious planet. Even today, despite modern telescopes and computer models, Neptune remains one of the least studied planets. At first glance, it resembles Uranus, being a similarly bluish sphere hidden beneath clouds. However, the difference becomes obvious. While Uranus is a calm and cold world, Neptune is a tempestuous giant, home to the most powerful hurricanes in the solar system. This planet is the true master of cosmic winds, and its history is full of enigmas. Like Uranus, Neptune is an icy giant, but its atmosphere is significantly more dynamic. Composed mainly of hydrogen, helium, and methane, it shares the same bluish hue. Yet, the most striking feature is the winds. Hurricanes on Neptune blow at speeds of up to 2,400 kilometers per hour, exceeding the speed of sound in Earth's atmosphere and 3 times more powerful than the most destructive hurricanes. Scientists still can't grasp how Neptune maintains such a turbulent atmosphere. The planet receives only 1/9 of the sunlight compared to Jupiter, and its upper layers appear cold and calm, but powerful storms and vortices rage deep within, moving at tremendous speeds. Neptune also has its own giant hurricane known as the Great Dark Spot. When a spacecraft first transmitted images of Neptune in 1989, scientists noticed a massive dark spot resembling a storm on Jupiter, stretching over 88,000 kilometers, with winds inside the hurricane reaching 2,000 kilometers per hour. However, a few years later, when astronomers redirected telescopes at Neptune, the dark spot had vanished. It simply dissipated. Later, new dark spots and other giant hurricanes were discovered, appearing and disappearing in Neptune's atmosphere every 5 to 10 years, making it the only planet in the solar system where enormous storms don't last for centuries, but come and go in mere decades. Like Uranus, Neptune lacks a solid surface. If someone tried to land on it, they would just sink deeper into the gas layers until the pressure crushed them. Unlike gas giants like Jupiter and Saturn, Neptune contains more ice and heavy compounds, such as water, ammonia, and methane. Beneath its dense atmosphere lies a thick layer of icy mantle, likely made of water ice and frozen ammonia. However, beneath this layer hides a core similar to Earth's, hot and dense, composed of rocks and metals, with temperatures reaching 7,000 degrees Celsius. This hot core helps sustain powerful winds and atmospheric activity, as Neptune emits twice as much heat as it receives from the Sun. Among Neptune's moons stands out Triton, the largest moon of the planet and one of the most unusual objects in the solar system. Its main feature is that it rotates in the opposite direction. Among all the moons orbiting planets, Triton is unique for moving in the reverse direction relative to Neptune. This indicates that it wasn't originally part of Neptune's system, but was captured by its gravity from the Kuiper Belt, a region filled with frozen bodies beyond Neptune's orbit. But that's not its only anomaly. Triton's surface is covered in nitrogen ice, with temperatures dropping to -235 degrees Celsius, making it one of the coldest objects in the solar system. However, the most astonishing feature is the icy geysers discovered by Voyager 2. These giant jets of nitrogen erupt from the surface, indicating a heat source within the moon that facilitates ice vaporization. Some researchers suggest that beneath Triton's icy crust could lie a liquid water ocean, similar to those on Europa and Enceladus. So far, Voyager 2 remains the only spacecraft to have visited Neptune. Since then, no other probes have been sent to this planet, but in recent years, astronomers have discussed the possibility of a new mission. One of the projects is the Neptune Odyssey, which could send an orbiter for detailed exploration of the planet. There's also the possibility of a Riden mission aimed at Triton to test the hypothesis of a subsurface ocean, but such missions would require decades, even if a probe launches in the next few years. It could only reach Neptune in 2040. Our study of the solar system's planets has come to an end, but the system itself doesn't stop here. Beyond Neptune lies the Kuiper Belt, which hides thousands of icy worlds like Pluto, Haumea, Makemake, and others. We've covered 8 planets, but between and beyond them lies a whole world of small bodies, asteroids, comets, dwarf planets, and meteoroids. These objects may seem insignificant compared to giants like Jupiter or Saturn, but their role in the formation and evolution of the system is hard to overstate. They hold information about the past, and some may pose a potential threat to Earth. When astronomers began systematic observations of the sky, they expected to find another planet between Mars and Jupiter, as the laws of dynamics suggested a large world should be located there. However, instead of a hospitable environment for life, solar wind, a stream of charged particles, interacts with the magnetic field of Earth, creating beautiful auroras. Despite its distance, the Sun's influence is essential for maintaining the balance of our solar system. It generates warmth and energy necessary for all living organisms. Without the Sun, life as we know it wouldn't exist. The Sun's gravity keeps planets in their orbits, ensuring stability. This gravitational pull prevents planets from drifting into space, allowing them to remain in a predictable path. Solar radiation not only warms the Earth, but also drives weather patterns and climate systems. This radiation is crucial for photosynthesis, enabling plants to produce oxygen. In conclusion, the Sun is more than just a star. It's the heart of our solar system. Its powerful processes and interactions sustain life and shape the environment. Understanding the Sun helps us appreciate its role in the universe. Life depends on this radiation. Without it, our planet's surface would freeze and the atmosphere would turn into a lifeless icy layer. Solar wind spreads from the Sun in all directions, affecting planetary atmospheres, interacting with magnetic fields, and creating auroras. At the farthest edge of solar influence, the heliopause, solar wind collides with the interstellar medium. Here, about 20 billion kilometers from the Sun, its influence ends and endless space begins. 4.5 billion years ago, the Sun started its existence and will shine for about the same duration. However, it isn't eternal. In 5 billion years, it'll begin to expand into a red giant, engulfing Mercury, then Venus, and possibly even Earth. After a few 100 million years, the Sun will shed its outer layers, leaving behind the white dwarf, a small but bright body. Yet, this won't happen for many billions of years, and as long as the Sun remains our primary source of life and energy, our system can exist. We began our journey by exploring the planets, and now it's clear that everything in our system is interconnected. In conclusion, this is a fascinating, complex, and dynamic system where each planet, moon, and even the most distant comets are linked by invisible threads of gravity, radiation, and energy from our star. Thank you for joining me on this exciting journey through our star system. I hope you learned something new and discovered amazing facts about space. If you enjoyed this journey, feel free to share your thoughts, ask questions, and keep exploring the universe. Space is infinite, so we have many more discoveries ahead.